So my name is Hiram Wright, and I'm going to be talking about some of the work we've done at Google along the lines of incremental type migration on using the basis of type algebras. Particularly this is in the time domain, and I want to, motivate this with a little bit of an example. So at Google, we have a lot of legacy code, and some of it looks like this. Right, so this is a fairly standard set of functions. It takes maybe a deadline and does some computation, and there are multiple things happening here in both the time and duration domains, using just integral and floating point types. So there's a variety of different things going on here, and it's very easy to make a mistake when you have this kind of code because it tends to be easy to misinterpret what exactly domain you're working in, whether it's duration or time. So we've introduced a stronger type library. And ideally, we'd like to get all of our code to look like this. We'd like to have stronger types to be able to do these computations in. But getting there is really difficult because of our large legacy code base. So we want to be able to, in order to do that migration, we want to automate almost everything. We're talking hundreds of millions of lines of C++ code. We want to keep everything buildable in each step. We can't, we have to do this piecewise because we can't do big monolithic migrations. We need to be able to keep code readable in each step, so engineers need to be able to interact with the code. We eventually want to converge on some fixed point. We don't want to be running these forever. So approaches that don't work, we've tried these. Monolithic changes. We can't change everything at once because the code base is just too big. We can't depend on variable type names to determine what the eventual type of a thing should be. How do we apply stronger types? Because most integers and floating points don't represent time. They represent something else. So we can't just migrate all the integers. Can't use variable names because they're ambiguous. We can't even use comments because they may not even be there. So we've exploited some of the facts of the time library that we're using. So the AppCell time library models time as a one-dimensional affine space. This means that time instants are a specific type, and time intervals are different types. So instants are points, intervals are vectors in the space, which then means that you can define various mathematical operations. So for instance, addition and subtraction are defined on this. This all comes from the affine space algebras. Addition and subtraction are defined, except for some notable exceptions, right? So you'll note that time plus time is undefined. It's nonsensical to add 2 points. You can subtract 2 points to find out the difference between them, but you can't add them. Similarly, there's duration minus time is undefined, and we'll exploit this fact a little bit later. There's other operations such as multiplication, division by scalars, comparisons. There's some distribution operations as well. And so we can then use this information to incrementally migrate our code base by performing a series of discrete steps across our code base. And we'll talk about some of these. So we can do, first of all, we start with expression simplification, expression-based things. We can do simplifications, we can do comparisons, additions, subtractions. Then move on to variable-based transformations, and these happen on a larger scale. So these are intra-statement kind of transformations. We can then go inter-function transformations, right, where we look at parameters and return values and things that span maybe translation units in terms of trying to update our code base. So let's take an example. So we can try to simplify expressions by consider this expression. We can just say like that should actually be, since we're taking a seconds value and multiplying it by 100 and we're converting it to milliseconds, we should actually just convert that directly to seconds, right? This is just a homogenization type of thing. We can also see like this simplification takes out the cast and converts to the second expression that we start with, and then that can also be converted. So we can see this kind of piecemeal, stepwise conversion process at work, and we can write discrete tools for each of these type of things. In the case of the cast master or the cast matcher, we're using these kinds of tools. So this is just an example of the compiler-based tooling that we're using. All of this is being done using static analysis, compiler-based tooling that we've talked about in the past. And it runs continuously across our code base in, so every night we can pick up new instances of each of these patterns and apply them. Similarly, we can change comparisons, right? So in this case, we know that we have a thing that's in the seconds domain on the left-hand side, and we can convert that to the seconds domain on the right-hand side. And again, that gives us the ability to perform potentially additional simplifications. And we move to something like addition. Note that here, if we know the type of 2 of the operands, we can infer the type of the third operand. So this is where some of this type algebra comes into play. Remember we had this table earlier on? Well, we can use this to then make additional simplifications. So in this case, we know the result of the expression is a time instant, and we know that one of the operands is a duration, and then we can infer that the other one must be a time instant because of the table we just showed. Similarly, there's a couple of cases in which the certain operations are undefined, so we can then narrow our focus even more and do additional inferences, even if we only have one type of an operand defined. Going on, we can do local variables. So for instance, we can take this variable timeout seconds. We can infer that it should be a second based upon the conversion function that's happening on the assignment. And then we can do contextual based transformations. So in this case, we have to transform the type and the constructor and the assignment constructor. But then we also have to look at sometimes it's being used in a context where it needs to be converted itself. Sometimes it's being used in a context where the L value itself needs to be converted. So we can do that based on the context of the things being used in. And we can change the name of the variable. Remember, we want to make this look like a human wrote it, right? So we can change the name of the variable. We can also do similar types of things for class members, right? And we do that. Interfunction parameters. We want to be able to look at the way that parameters. This is similar to doing local variables, and now we're expanding beyond the context of a single function. We're moving to different parameters, or to changing parameter types, right? So in this case, we can change the type of the parameter, and then we can change its callers. Now, how do we start off with time type information? That's one of the problems. Well, we first want to seed this information so we can identify specific calls throughout the code base and use those to then seed this type information across our code base. That's a process that we've done throughout our code base. We've changed tens of thousands of callers, and that's given us the context by which we can do this kind of information. And occasionally we run into this case where we get bugs and people wonder what's going on, and we're saying we're translating your code by what it currently does, not what it meant to do. So the practical example, you can see us working through this, right? We're adding things, we're migrating through this. And this is very quick because I don't have a lot of time here. The reactions to all this process have been mixed. Some people have said, you've added a bug, and then, oh no, wait a minute, the bug was already there and we can address it. Some people have been very appreciative. Most people haven't said anything, which is really how we know we've done our job. We've been able to translate their code in a way that's transparent to them and maintain semantic correctness while still adding strong types. There's the contact information, there's the source code, and thank you. The further information is available in the paper. Thank you very much.